This is the equation we want to solve. Let's consider the function of x, that is x squared minus 2x minus 10, and see what values it takes for various values of x. We'll keep track in this table. Here are some values for x. Let's start with x equals 0, as that might be easy to calculate. Then x squared equals 0, and 2x is also 0, so the value of the function is just negative 10 from this constant part. For x equals 1, x squared minus 2x minus 10 is 1 minus 2 minus 10, or minus 11. And for x equals 2, the function takes the value 2 squared is 4 minus 2 2's are also 4 minus 10, giving negative 10. The other values of f of x can be found, and if a graph of y equals f of x is plotted, it looks like this. Notice that the graph has a minimum at x equals 1, y equals negative 10. More importantly for our application, notice that the graph crosses the x-axis twice. This is where y equals f of x is equal to 0. But x squared minus 2x minus 10 equals 0 is exactly the equation we're trying to solve. So the points at which the graph crosses the axes are the solutions of the equation. We can see that the solutions are x equals 4 and a bit and negative 2 and a bit, which tally with the algebraic approach we took in the previous video. Now let's try to solve this similar but modified equation. Notice that the constant term in the equation is now plus 10 rather than negative 10. When we work out values for f of x at different values of x and plot them, this is what we get. In the previous video on the algebraic approach, we said that the equation had no real solutions because it required the square root of a negative number. In this more graphical approach, we can see that this is equivalent to saying that the equation has no real solution because the graph of y equals f of x does not cross the x-axis.